Quantum computing promises to revolutionize the way we solve problems. The advantages that come from solving hard problems in this fashion are colossal. But there's still a long way for us to go to actually demonstrate solving a functionally useful problem. The main reason for this is the amount of qubits that we need. Companies like Google and IBM have quantum processors, but these only have tens to hundreds of qubits, with the most currently held with IBM's Eagle quantum processor with only 127 qubits. The issue being, for complex problems, we need error correction. This dramatically increases the number of qubits that are required. One of these error-corrected qubits, which are often referred to as logical qubits, can contain thousands of physical qubits. Thus, we need to find methods to build large numbers of qubits to find any practical application of quantum computing. In this latest work from a team at MIT, they've turned to using two-dimensional materials to help solve this problem. This holds significant promise in terms of scaling down the qubits to as small as they can possibly be. So how did they do it? Let's discuss it. Superconducting qubits come in many forms, but they all contain one similarity, that is, a Josephson junction. This acts as a quantum connector between two pieces of superconductor. The Josephson junction is formed when two superconductors are brought into proximity with each other, and then they are weakly connected. This can either be through physically connecting them, to say, having two superconductors with a nanowire in between them, or it can be through building a barrier between the two, so that tunneling has to occur between the two superconductors. Sometimes this barrier can be formed through a vacuum, but this has issues, namely that the electric field that can be produced between the two can spread far over the sample, and therefore crosstalk can happen between qubits. This ends up resulting in qubits having to have large spacing in between them so they can perform well. So ideally, we would replace this vacuum with an insulating material. But herein lies the problem. A lot of classical insulators have a lot of defects in them, and these defects destroy the properties of the Josephson junction. One of the lead researchers described it as this. Most common dielectrics used in integrated circuits, such as silicon oxides and silicon nitrides, have many defects, resulting in quality factors around 500 to 1,000. This is simply too lossy for quantum computing applications. So to overcome this issue, the scientists turned to the realm of 2D materials. There are many different 2D materials, and more are discovered every year. It was only in 2004 that graphene was first isolated, and this sparked a fevered search for more materials that behaved in a similar fashion. Importantly, when electrons are confined to a two-dimensional plane, they behave differently. As such, two-dimensional materials hold a lot of promise for many different applications, as we can find two-dimensional materials that are superconductors, insulators, magnets, and many more. One material that's garnered a lot of attention is hexagonal boron nitride, also referred to as HBN. This two-dimensional material has the same hexagonal structure as graphene, but rather than being a metal, it's an insulator, and an extremely good one at that. These researchers took a crystal of HBN and performed the same experiment that was done on graphene back in 2004. That is, they took a piece of tape and exfoliated off layers of this two-dimensional material. They then took a second piece of tape and then further removed more layers, and so on and so forth until they got down to a monolayer. Now things have gotten a little bit more sophisticated since 2004. Rather than tape, it's a polymer, and this can be placed with a lot of precision and also controlled through temperature. Additionally, this is now often done in glove boxes, where a glove box is a large container which has a higher pressure than atmosphere, often with an inert gas like nitrogen and argon, to create a clean environment. This is very important for these materials, because while graphene is very stable in air, many 2D materials are not, and when exposed to oxygen, degrade very quickly. HBN is also one of these two-dimensional materials that is very stable, and is often used to seal these volatile 2D materials to stop them from interacting with the atmosphere. One of the lead scientists said this: "One of the biggest challenges of the fabrication process is working with niobium diselenide, which will oxidize in seconds if exposed to air. To avoid that, the whole assembly of this structure has to be done in what we call the glove box. So to make a superconducting qubit out of 2D materials, the scientists first laid down one layer of superconducting material, the niobium diselenide, and then placed a layer of the HBN on top. They then placed a final layer of the niobium diselenide on top of this. In this fashion, the HBN becomes the barrier between the two superconducting layers, forming a Josephson junction. They then cooled the sample down to around 10 millikelvin, which is 0.01 degrees above absolute zero. They did this so they can perform tests on how these qubits perform similar to normal qubits. The temperature needs to be this cold for a few reasons. The first is the niobium diselenide doesn't become superconducting until below 7 Kelvin. The second is to combat noise. Noise can come in a few different forms. It can be through defects that are activated in the HBN or in the superconductors themselves, but it can also come in just thermal noise, which are often referred to as phonons. And these phonons can interact with the qubit itself, destroying its coherence and therefore its qualities as a qubit. In the end, the great news is this technique worked. They were able to demonstrate that their qubit that was fabricated with two-dimensional materials that was 100 times smaller than the traditional qubits that were also fabricated on the sample performed in a similar fashion. And this demonstrates that two-dimensional materials are a good source of fabricating these types of qubits. But there's still a long way to go. Building superconducting qubits in this fashion is extremely time-consuming and not very reliable. This might be okay if you've got a PhD student that's willing to spend months just to fabricate one qubit. But to be practically useful, we have to find new methods. Two-dimensional materials are amazing, but they're very difficult to work with, and many of them are very difficult to scale up. So while this is a very interesting and promising result, there's still a long road ahead until we see this as a functional technique for fabricating a large number of superconducting qubits for a quantum computer. Thanks for watching. Have fun. See you next time.